Hello students, this is a second lesson on waves. So I want you to stop if you haven't already completed the first lesson, please go back and do that one. Otherwise this might not make as much sense as it would have otherwise. So in the first lesson we kind of learned like what are waves, how do we classify them. We learned there's two different ways of classifying. And they're both meaningful. One would be like on the form it takes, so its formation either being from an up and down motion that creates a wave in the perpendicular direction, or in a back and forth motion that creates a wave that goes out in that direction, the same direction as the wave. Those are the two different ways of classifying it by its form. The other way we classify waves is by whether it needs a medium, which is like something to travel through or not. So most waves are mechanical, but light is electromagnetic. Basically, light is its own thing, and then you have mechanical waves that need to move through things in order to basically be waves. So, all right, just real quick, I want to remind you to have your guided notes open, which you can find at the bottom of the assignment. So, guided notes, in this one, I really do want you to get a pencil and paper, or a pen and paper. You can do a couple sketches. Try and use like the whole page for this, basically just for this diagram. Try and do your best job of drawing it. It doesn't have to be perfect. Basically, it's just going to be something that's helpful for you to try and fill out as you go along in taking notes. So as we talk about amplitude, try and make sure you've labeled it. And then down further, there is a answer key down here. Just try and do your best first, and then match it up to understand. Trust me on that one. It's definitely worth doing. And then if you don't understand it at the end, at least you'll know what you don't understand, instead of just copying it and not really being sure if you really understood it or not. So let's get started here. The properties. What are the things that make waves waves? We'll be talking about all the other types of waves we talked before. We're just going to actually start describing them in a little bit more detail. That is the question. So before we start also, besides getting a pencil and paper, I should have told you to go get like a string, rope, slinky, shoelace, basically anything that you could turn into a wave. And just like this handy dandy picture here, just try and attach it to something, whether it's tying it to a doorknob or to the bottom of your chair, and you can get out of your seat and practice that way. It's basically something that you can push up or down and push front and back to create a wave in. Typically in school we use slinkies for this. Slinkies happen to be awesome. You have like your kid brother or sister holding one side if you want it, as long as they don't go crazy and break anything. So I'm going to assume that at this point you have that and you're ready to go. If you don't, it's okay. You know, it's just hopeful. You can kind of hopefully imagine it otherwise. So the first thing we're going to talk about are some things that are most essential. So amplitude. Amplitude is really the measurement of the height of a wave, but it's not just the height of a wave. It's more of like how much energy is getting pushed through this matter right now. And the way that we measure that is by using this thing called amplitude. So hey, you got a lot of energy in that sound wave or a lot of energy in that light wave. How do you know? We measure the total displacement from the rest position. So this little line here is kind of like, if you had a pond, say, right? And the pond was still, it would look like this. If you dropped a big stone in there, it would dip down a lot. If you dropped a small stone, it would dip down just a little bit. And basically that change in distance from where it was before, your moving matter, that takes energy. That's how we measure the energy. So that's either this way or that way. And a lot of times it becomes this and then it goes back down. So does it make a difference if you're measuring the top to the bottom, or the bottom to the middle, I should say, or the top to the middle? No. It's basically just the height of displacement from the very farthest it gets away from rest position to this little middle line here. That's in a transverse wave. Those are the ones that go up and down. All right, the back and forth waves, the longitudinal waves, and if you don't know what I'm talking about with longitudinal or transverse, please make sure you go back to that first video. Longitudinal waves, where you'd be pushing front and back. Basically, if you imagine crushing with a lot of energy, you'd end up with this big compression zone where, say in a slinky, you'd actually see that compression moving through And the more compressed it is, the more stuff you've compressed, basically the more energy is transferring through that. We'll take a look at that in a minute. Rarefaction is kind of the opposite of that. We don't necessarily measure it to say, hey, how much energy is there? This is, I mean, if you're stretching, it takes just as much energy as it does to compress it. But typically we say that the amplitude is that the distance from here to here. It's basically just saying, hey, this is how much stuff you're crushing. That's how much energy there must be. Or in a transverse wave, oh, it goes down that much from where it was. That is the total amount of energy in that wave. So just working off of that, if you have a wave with a small amplitude, meaning there's not a huge amount of displacement from that middle line either way, then it doesn't have as much energy as a wave that has high amplitude. And high not just meaning this way, but high as in it's very far away on both sides from the rest position. Now if you have a chance, if you have tied up your string, just try and make a low energy wave and a high energy wave in terms of their amplitude. And you can see it takes a lot more energy to get the thing to go up and down a lot than it does to go over a small distance this way. Okay, the next property we'll talk about is wavelength. Now wavelength is just basically a measurement from one point on the wave to where it repeats again. So it's the distance between two crests or troughs in a wave. This could be from the top to the top, the bottom to the bottom, the middle to the middle. But just be careful. A full wave is a full cycle, so it goes up and down and then back to where it started from. If you were to measure from here to here, from one place to where it bends is called a node, that wouldn't be a full wavelength. That would only be half of the wave because it's not actually it's not back to where it really started from because the energy is moving in this direction instead of this direction. So the full wave, just to make sure you don't confuse where the nodes are, just measure it from the crest to the crest or the trough to the trough. We'll talk about what those two things are later. Basically, it's the easiest way of doing it for a transverse wave. Longitudinal waves, the wavelength is basically from where it starts to where it looks like it's copied to, right? So if this wave starts here and then starts here again, the wavelength would be from the very front of this to the very front of this, or the very back of this to the very back of this. In either case, it's just measuring, hey, how long is that full up and down motion or front and back motion? How wide is that? How long is it? In terms of transverse waves of light, wavelengths are actually really important to us. All the color that you see, the only thing that makes a difference between red and blue, or even X-rays and gamma radiation, microwaves and radio waves, is the wavelength of the light. So as the electromagnetic fields create basically that light moving, that photon moving, we're just going to imagine it real quick to simplify it, that it just goes up and down in a wave. It's not really like that in real life, but it's just certainly a lot less complicated. So as it goes up and down, the distance between the peaks or the troughs, basically the wavelength, determines how our eyes see it as color. If you can imagine that a meter, which is about, I'm probably 2 meters tall, right? So this would be 700 billionths of a meter is one full wavelength of red light that we can see. So your eyes aren't able to necessarily see the light down that small, but that's what our eyes are able to process, all the way up to about 400 nanometers, so 400 billionths of a meter long. So most light is not just visible light. A lot of it's much longer than that. It can be miles long, or it could be much, much smaller than that in terms of its wavelength. The smaller the wavelength is, generally the more energy you have. Not generally, you always have more energy if the wavelength is tighter. If you could imagine trying to make a wave with a shorter wavelength, go ahead and try and do that right now with your little setup. Okay, so if you're trying to make short wavelengths, you notice you actually have to put a lot more energy into it to get those wavelengths to be tinier. Basically, one long wavelength you don't have to do very much with, but a lot of short ones takes a lot of energy. That's why light that has a short wavelength will typically be more and more and more damaging to us. Ultraviolet radiation or light is a little bit shorter in wavelength than blue light or violet. That's why I call it ultraviolet. It's a little bit shorter. It becomes damaging. Basically, since it's going back and forth so much, as it goes into your skin or wherever, it actually hits all the stuff in there instead of just going into it and getting absorbed in different ways. X-rays are even worse. Gamma rays kill you. All right, so like I said, of the whole spectrum, we say it's the electromagnetic spectrum, and we've talked about this many times, the wavelength, how long between the peaks of these waves determines what it does, basically. This is really, really important for light, which we have this small little inkling of for visible light. In terms of sound, sound is a longitudinal wave, so it doesn't look like this, but you certainly hear it as being different depending on how long that wave is as well. Okay, so if you're looking at this picture, for instance, right up here would be violet, dark violet, which is about 400 nanometers of light, wavelength of light. You can hardly see it, and even down here, dark red, which is 700. Basically, beyond that, you know, things do produce light that's invisible to us. Most of the light out there is. Below red, you would start to have infrared, which you can sometimes feel if you ever feel a toaster, right? But you don't see it actually glowing. That's infrared light that's coming out and hitting you. So once again, really important idea here is that the shorter the wavelength is of a wave, the more energy it's going to be storing. It just takes more energy to move matter that much more quickly. It's kind of like more powerful if you want to think about it like that. Frequency. And this is, I really feel bad because this is a really hard one to explain over video. But basically frequency is kind of a match of like wavelength itself, like how far is it between here and here, and how fast is that happening. So if you have multiple waves per second, your frequency would be higher. And that only happens when your wavelength is shorter for light. If you have a long wave, well, if it's traveling very fast, you might have a higher frequency, but typically the longer the wave length is, the lower the frequency is going to be. In terms of sound, the frequency is how high or how low, like high or how low it is in its pitch. But for light, the frequency is directly related to the wavelength, and it's the color of it. These two equations here, typically we would have done an experiment to kind of prove this with a pendulum even. A frequency of a pendulum would be how often it goes back and forth. One back and forth motion would be like a cycle. You say that's 1 cycle per second. And that is what a hertz is. That's the unit for that. So I know it's kind of hard to explain it right now like that, but frequency is a measurement of how many waves per second. And we measure that in what's called a hertz. So once again, the higher the frequency, the shorter wavelength, the more energy you have in a wave. Now, wave speed itself isn't how fast it's going up and down, it's how fast it's moving out in the direction it's going in. So the speed of light is always the same. It doesn't matter if it's ultraviolet light or visible light or radio waves, it's always the speed of light, which is incredibly fast. But the wavelength of it, if you imagine that you have a wavelength that's very short, if it's going up and down a lot over the same distance, over the same speed as another one, you end up with a higher frequency. It just goes up and down more often. So wave speed depends on basically the wavelength, and it can indicate also, it depends, it depends on the wavelength itself and on the medium it's traveling through. For light, it travels very fast. It doesn't need to travel through a medium, but depending on the medium itself, it could change how fast the wave is going to pass through it. Now, I'd like you to think for a second. Do you think that a less dense medium or a more dense medium would create a faster wave? Say again, if that wave is going through something that's more solid or something that's less solid, more wispy, dense, undense like gas, which would it travel faster through? Okay, the answer for that one is through a more dense medium. And I'm going to stop the video here for now.